Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today we're going to be continuing chapter 4. So far we've defined entropy and we have covered the second law of thermodynamics. The next thing we're going to do is apply what we've learned to calculate entropy changes in different systems, including mixing of ideal gases, phase transitions, and heating. The first thing we're going to begin with is the mixing of ideal gases. So let's imagine that we start with two separate containers. In the first container, we have gas A with Na moles occupying a volume of Va at temperature T and pressure P. In the second container, we have gas B with Nb moles in a volume of Vb, also at the same temperature T and pressure P. Initially, these gases are going to be separated by a partition. But when that partition is removed, the two gases are going to expand into the combined volume V, which equals Va plus Vb. And what we'll get is a uniform mixture. So what is the entropy change for this mixing process? Let's analyze it step by step. For gas A, before mixing, it's going to be confined to its own volume Va. After mixing, it's going to be able to access the full combined volume Va plus Vb. This looks just like the isothermal expansion problem we worked through previously, except now the final volume is the combined container. So the entropy change for gas A is given by delta SA equals Na times R times the natural log of Va plus Vb divided by Va, where Va plus Vb is that final combined volume. By the same reasoning, gas B expands from Vb to the combined volume Va plus Vb. So its entropy change is delta SB equals Nb times R times the natural log of Va plus Vb divided by Vb. The total entropy change for mixing, delta S mix, that's simply going to be the sum of these two contributions. So delta S mix equals delta SA plus delta SB, which expands to delta S mix equals Na times R times the natural log of Va plus Vb over Va plus Nb times R times the natural log of Va plus Vb over Vb. Now, let's simplify this expression. So at constant temperature and pressure, the volume of an ideal gas, that's going to be directly proportional to the number of moles present. That means Va is proportional to Na, and Vb, that's proportional to Nb. So we can go ahead and replace the volume ratios with mole ratios. So doing that gives us delta S mix equals Na times R times the natural log of Na plus Nb over Na plus Nb times R times the natural log of Na plus Nb over Nb. Now let's rearrange this into a more compact form. Notice that each term actually looks like a negative log of a mole fraction. So if we define the mole fraction as Xa equals Na divided by Na plus Nb, and we define Xb to be equal to Nb divided by Na plus Nb, then we can use that formula and rewrite our expression. Our equation now becomes delta S mix equals negative Na times R times the natural log of Xa minus Nb times R times the natural log of Xb. Or in its final compact expression, we can take out the common factor minus R, and that way we can write delta S mix equals negative R times the sum of Na times the natural log of Xa plus Nb times the natural log of Xb. This is the entropy of mixing for two ideal gases. Now, there are a few important things to note here. First, the entropy of mixing is always positive because the mole fractions are less than 1 and the natural log of a number less than 1 is negative. Multiplying by the minus sign makes the whole expression positive. And that makes sense. Mixing increases disorder and it creates more microstates, so entropy must increase. Second, notice that the formula, it does not depend on the identity of the gases at all. As long as they are ideal and they're different from each other, the entropy change depends only on the mole numbers and their ratios. This is one of the elegant features of statistical thermodynamics. Finally, you might wonder what happens if the two gases are identical, like oxygen with oxygen. At first glance, our formula seems to suggest a positive entropy change since we're still combining two volumes. But in reality, nothing changes. The final state is indistinguishable from the initial one because all of the particles are identical. There's no new distinguishable arrangements that are created by removing the partition. So in fact, the entropy of mixing is 0. Now, this scenario is actually called the Gibbs paradox, and the entropy of mixing, we need to note here, only applies when the gases are different in identity. So to summarize, the entropy of mixing is given by this expression, delta S mix equals negative R times the sum of Na natural log XA plus NB natural log XB. It's always positive for the mixing of different ideal gases, and it captures the increased disorder that arises from combining systems that were initially separate. Next, let's discuss the entropy of phase transitions like melting and vaporization. Phase transitions are special because they happen at constant temperature and constant pressure. During phase transitions, the heat that's absorbed is being used to break intermolecular interactions and reorganize the system into a new phase. So how do we write the entropy change for such processes? Remember that the general definition is ds equals dq reversible divided by T. At constant pressure, the heat that's absorbed during a reversible phase change, that is equal to the enthalpy change of that transition. So for fusion or melting, the reversible heat is equal to delta H fusion, which is the enthalpy of fusion. So that means we can write delta S fusion equals delta H fusion divided by TF, where TF is the melting temperature. For vaporization, the reversible heat is equal to delta H vap, which is the enthalpy of vaporization. So we can write delta S vap equals delta H vap divided by TB, where TB is the boiling temperature. These two equations, they tell us something very important. They show that entropy changes during phase transitions. They depend only on how much heat is required to complete the transition and what temperature it occurs. Also notice the physical meaning. Melting or vaporization greatly increases the number of accessible microstates for the molecules. A solid has molecules that are locked into position with limited freedom. A liquid allows translational motion, and a vapor allows nearly complete freedom of motion. It's also worth pointing out that these formulas apply just as well to the reverse processes like freezing and condensation. So take liquid water freezing into ice as an example. In this case, the system gives off heat equal to the enthalpy of fusion, and the entropy change is going to be negative because the molecules become more ordered in the solid lattice. Similarly, when a vapor condenses into a liquid, the system releases the enthalpy of vaporization, and the entropy change is negative delta H vap divided by temperature. So The key idea is that the formulas themselves are not tied to one direction. What matters is the sign of the heat flow and whether the molecular disorder increases or decreases. Melting and vaporization, those are associated with positive entropy changes, while freezing and condensation are associated with negative entropy changes. Therefore, entropy changes during phase transitions give us a direct measure of how molecular freedom changes when matter shifts between solid, liquid, and gas. Finally, let's think about what happens when we simply heat a substance without changing its phase. When the temperature of a system increases, the entropy also increases. But why? The answer is simple, because raising the temperature gives molecules access to more energy states. More vibrational levels become populated, more rotational states are occupied, and the distribution of molecular motions broadens. All of this means more microstates and higher entropy. Now, the general definition again is ds equals dq reversible divided by T. If we integrate this from the initial temperature T1 to a final temperature T2, we can write the entropy at T2 as S2 equals S1 plus the integral from T1 to T2 of dq reversible over T. Now, if we specify that this is a constant pressure process, then the heat added reversibly, that's going to be equal to the change in enthalpy, dH. And at constant pressure, that can also be written as Cp dt, where Cp is the heat capacity at constant pressure. So the integral becomes S2 equals S1 plus the integral from T1 to T2 of Cp divided by T dt. If the temperature range is small, we often treat Cp as a constant so that it is independent of temperature. So then in that case, the integral actually simplifies and we get S2 equals S1 plus Cp times the natural log of T2 over T1. Therefore, the change in entropy due to heating is delta S equals Cp times the natural log of T2 over T1. You can also write this as delta S is equal to the number of moles N times molar Cp times the natural log of T2 over T1. This is a very powerful result. It tells us that entropy increases with temperature in a logarithmic fashion. Why is this important? Well, because it shows that entropy isn't just about mixing or phase changes. It is also fundamentally tied to how a system responds to heating. Heat capacity, which we measure in the lab, directly determines how much entropy increases when you raise the temperature. So this links entropy to something tangible and measurable, and that is very much a cornerstone of calorimetry in physical chemistry. With that, let's jump into a practice problem. This one says, at constant pressure, 200 grams of water is heated from 10 degrees Celsius to 20 degrees Celsius. Calculate the increase in entropy for this process. The molar heat capacity of water at constant pressure is 75.3 joules per Kelvin per mole. Now, in this problem, we are given information on the molar heat capacity at constant pressure, and we're also given the temperature change. It's from 10 to 20 degrees Celsius. These two pieces of information help guide us in which equation to use to solve this problem. In addition, you'll notice that the temperature change here isn't super large. In those cases, we can treat Cp as being temperature independent. So for these 10 degrees, that's going to be perfectly fine approximation. This is going to allow us to set up that delta S is equal to N times molar Cp times the natural log of T2 over T1. From there, we need to figure out what the number of moles is from the information we're given. We have 200 grams of water. If we divide by the molar mass of water, which is about 18.02 grams per mole, we get 11.1 moles of water. We also want to convert temperature to Kelvin. 10 degrees Celsius is 283 Kelvin. 20 degrees Celsius is 293 Kelvin. Now we can plug everything into our equation. Delta S is equal to 11.1 moles times 75.3 joules per Kelvin per mole times the natural log of 293 over 283. Multiplying through gives approximately 29.0 joules per Kelvin. The sign is positive, as it should be. Heating increases the number of thermally accessible energy states, so entropy rises. Let's tackle one more. This problem says supercooled water is liquid water that has been cooled below its normal freezing point. This state is thermodynamically unstable and it tends to freeze into ice spontaneously. Suppose we have 2 moles of supercooled water turning into ice at negative 10 degrees Celsius and 1 atmosphere. Calculate the values of delta S system, delta S surroundings, and delta S universe for this process. The molar Cp values of water and ice for the temperature range between 0 and negative 10 degrees Celsius are 75.3 joules per Kelvin per mole and 37.7 joules per Kelvin per mole, respectively. And the molar heat of fusion of water is 6.01 kilojoules per mole. Let's organize everything before we start calculating. The actual snap freeze of supercooled water at minus 10 degrees is irreversible because the system at minus 10 is not at the equilibrium temperature where liquid and solid coexist. However, entropy of the system is a state function, so we can actually replace the real path with any convenient reversible path that starts at the same initial state and ends at the same final state. And here we're going to use 3 reversible steps. 1, we're going to warm the supercooled liquid from minus 10 to 0 degrees at constant pressure. 2, we're going to freeze reversibly at 0 degrees where liquid and ice are at equilibrium. And then that 3rd step, we're going to cool the newly formed ice from 0 back down to minus 10 at constant pressure. Then by adding the entropy changes for these 3 steps, we're going to be able to get the system's total entropy change for the real process. So with that, let's begin our calculations for the entropy of a system. Step 1 is to warm the liquid from minus 10 degrees Celsius to 0 degrees Celsius. For heating at constant pressure, the entropy change is the integral of Cp over T dt, which for a small range with nearly constant heat capacity, that becomes number of moles times molar Cp times the natural log of final temperature over initial temperature. Converting to Kelvin, the initial temperature is 263 Kelvin and the final temperature is 273 Kelvin. We have 2 moles of water, and the molar Cp for liquid water is equal to 75.3 joules per Kelvin per mole. So then we write delta S for path 1 is, and the system is equal to 2 times 75.3 times the natural log of 273 divided by 263. And that gives us plus 5.6 joules per Kelvin. The sign is positive because warming broadens the population of energy levels. Now we're going to move into step 2, where we freeze at 0 degrees. Again, we're still calculating the entropy change for the system. At the equilibrium temperature of the phase change, the reversible heat equals the enthalpy of fusion. And going from liquid to solid releases heat, so the system's entropy change is the negative of enthalpy of fusion divided by the transition temperature. So we are given that delta H value. We're told that the molar heat of fusion of water is 6.01 kilojoules per mole. If we convert that to joules per mole, it is equal to 6,010 joules per mole. So we're going to plug that in to calculate delta S for path 2 for the system. This will be equal to 2, that's the number of moles, multiplied by negative 6,010 joules per mole divided by 273 Kelvin. For that, we're going to get minus 44.0 joules per Kelvin. The negative sign reflects the increased ordering in the solid. Then for step 3, we're cooling the ice from 0 to minus 10. Again, we're going to use the constant pressure heating formula with the heat capacity for ice. We are told that is 37.7 joules per Kelvin per mole. And we're going to reverse the temperature ratio here. So the result is that the delta S for path 3 for this system is equal to the number of moles, 2, multiplied by the heat capacity for ice, 37.7 joules per Kelvin per mole, times the natural log of T final divided by T initial. T final is 263 Kelvin, T initial is 273 Kelvin. And that's going to give us minus 2.8 joules per Kelvin. Now we're going to add the 3 pieces for the system. Delta S system will be equal to 5.6 minus 44 minus 2.8, and that is approximately minus 41.2 joules per Kelvin. That negative value makes sense. The system becomes more ordered overall, going from liquid into ice. Next, we're concerned with the surroundings. To calculate the value of delta S surroundings, we have to determine the heat change in the surroundings for each of the above steps. So during step 1, the system absorbs heat to warm the liquid. Therefore, the surroundings lose the same amount. So we're going to calculate Q surroundings for that first path. It will be equal to negative N times molar Cp of the liquid times delta T. So this is equal to negative 2 times 75.3 times 273 minus 263. And that calculation is equal to negative 1.5 times 10 to the 3 joules. Then during step 2, the system freezes at 0 degrees and it releases latent heat to the surroundings. So Q surroundings for path 2 is equal to positive N times delta H fusion. So this is equal to 2 times 6,010, which is approximately 1.2 times 10 to the 4 joules. Then during step 3, the ice cools and again releases heat. So Q surroundings for path 3 is equal to positive N times molar Cp ice times delta T, and that is approximately equal to positive 7.54 times 10 to the 2 joules. Then we're going to add up all of the Q surroundings total. So negative 1.5 times 10 to the 3 plus 1.2 times 10 to the 4 plus 7.54 times 10 to the 2. And that is approximately 1.1 times 10 to the 4 joules. With this value, we can calculate the change in entropy of the surroundings at negative 10 degrees Celsius or 263 Kelvin. So delta S surroundings is equal to Q surroundings total divided by 263. That's 1.1 times 10 to the 4 joules divided by 263 Kelvin. Our delta S surroundings is approximately 41.8 joules per Kelvin. Finally, The universe is going to be the sum of system and surroundings. So delta S universe is negative 41.2 plus 41.8, and that is equal to 0.6 joules per Kelvin. And with that, we have answered the problem fully. We are now ready to move into our next objective, where we're going to discuss the third law of thermodynamics. The third law of thermodynamics says, as the temperature of a perfect crystal approaches absolute zero, its entropy approaches zero. Why? Because at 0 Kelvin, a perfect crystal is completely ordered. Every molecule sits in a single well-defined arrangement. And in statistical language, there's only one accessible microstate. If the number of microstates is 1, then entropy equals Boltzmann's constant times the natural log of the number of microstates. So that becomes Kb times the natural log of 1. And the natural log of 1 is 0. So entropy is equal to 0. That's the key idea. Perfect order means no alternative arrangements to count. So entropy vanishes in the limit of 0 Kelvin. Now, in real materials with some orientational disorder or defects, there can be a tiny residual entropy, but for our thermodynamic foundations, we take the third law reference as 0 at 0 Kelvin for a perfect crystal. And this matters enormously because it fixes the 0 of the entropy scale. And with a firm reference point at 0 Kelvin, we can then talk not only about changes in entropy, but about the absolute entropy of a substance at any temperature. How do we get that value in practice? Well, we can imagine warming a sample up reversibly from 0 Kelvin up to our temperature of interest at constant pressure. And we can add up the entropy that's gained along the way. The differential definition says ds equals reversible heat divided by temperature. At constant pressure, the reversible heat for a temperature step is Cp times dt. So the incremental entropy is Cp divided by T times dt. And if we integrate that from 0 to our final temperature, we would get the entropy that's produced by warming within a single phase. Now, entropy is extensive, so if you have multiple moles, you can scale by the number of moles. If you have a mixture, you can sum the contributions for each component. Of course, when we actually heat a real substance from 0 Kelvin, we're usually going to cross phase transitions like melting and boiling. At each transition, the temperature is fixed while the substance absorbs or releases the latent heat associated with that change of phase. So here, the entropy jump is just enthalpy of the transition divided by the transition temperature. We saw this earlier. If you then want to sketch entropy versus temperature, you're going to see two sorts of regions. You're going to have smooth rise within each phase. So in these regions, you're going to be able to calculate entropy as the integral of Cp over T dt. And then you have these vertical steps at the melting and boiling points. Here you would calculate entropy as the enthalpy of that transition divided by the temperature of said transition. Physically, this plot essentially encodes two ideas at once. First point, as you warm within a phase, more energy levels become populated, so entropy rises gradually. And the second point is when you change phase, the freedom of molecular motion jumps when you move from solid to liquid to vapor, so entropy increases suddenly. And put together, the general recipe for the absolute molar entropy at some temperature T, you can get that by treating each segment appropriately that you pass through. So you would use the correct equation for heating at one particular phase, and you would use the appropriate equation for phase transitions, and you would calculate out each segment you would pass through going from an initial temperature to a final temperature, and then the total would be the sum of all of those pieces. And because The third law gave us the reference point at 0 Kelvin. This sum is going to yield an absolute value. Finally, once we know absolute entropies for substances, we can evaluate entropy changes for chemical reactions directly from tabulated values. So for a reaction written as A moles of reactant A plus B moles of reactant B gives us C moles of product C plus D moles of product D, the standard reaction entropy change at the tabulated temperature is going to be equal to the following expression. Delta S standard equals the total standard molar entropy of the products weighted by coefficients minus the total standard molar entropy of the reactants weighted by coefficients. So with that, let's try to apply this equation to a practice problem. This problem says, calculate the entropy change of the system, the entropy change of the surroundings, and the entropy change of the universe for the synthesis of ammonia at 25 degrees Celsius. The reaction is 1 mole of nitrogen gas reacts with 3 moles of hydrogen gas to produce 2 moles of ammonia gas. And the standard reaction enthalpy for this is negative 92.6 kilojoules per mole at 25 degrees Celsius. We're also given the standard molar entropies at this temperature. So for nitrogen gas, it's 191.6 joules per Kelvin per mole. For hydrogen gas, it's 130.6 joules per Kelvin per mole. And for ammonia, it's 192.5 joules per Kelvin per mole. Let's begin with the system. Delta S of the system equals the total standard molar entropy of the product, weighted by coefficients, minus the total standard molar entropy of the reactants, weighted by coefficients. So here, that's going to be 2 times the standard molar entropy of ammonia, minus this quantity that we're going to write in brackets, which consists of 1 times the standard molar entropy of nitrogen plus 3 times the standard molar entropy of hydrogen. Numerically, this is 2 times 192.5 joules per Kelvin per mole minus, in brackets, 1 times 191.6 joules per Kelvin per mole plus 3 times 130.6 joules per Kelvin per mole. Calculating this gets us 198.4 joules per Kelvin per mole. The negative sign makes sense. We've gone actually from 4 moles of gas on the reactant side to 2 moles of gas on the product side. So the number of gas phase degrees of freedom, and therefore the entropy of the system, drops. Now for the surroundings, its entropy change equals the heat it receives divided by its temperature. At constant pressure, the heat exchanged by the system for a reaction is the reaction enthalpy. Because the given enthalpy is negative, the system releases heat, and the surroundings, they absorb the same magnitude. So delta S of the surroundings equals minus delta H of the reaction divided by the temperature. Substituting the numbers in gets us minus of the negative 92.6 kilojoules per mole divided by 298 Kelvin. Now, if we want to make sure we get our answer in units of joules so that it matches the answer we got for delta S system, we want to go ahead and multiply 92.6 kilojoules per mole by 1,000. That's going to get us 92600. So that's 92,600 joules per mole. Plugging that in, we get approximately plus 311 joules per Kelvin per mole. Finally, the entropy change of the universe is going to be the sum of these 2 contributions. Delta S of the universe equals delta S of the system plus delta S of the surroundings, which is negative 198.4 plus 311. Plugging that into our calculator gives us about plus 113 joules per Kelvin per mole. And that is our final answer for this problem. What should we conclude? Now, even though the system's entropy decreases, because we produce fewer moles of gas, the heat increased for the surroundings. The heat released to the surroundings increases the surroundings' entropy by a larger amount. So we notice that the net change for the universe is positive. Up until this point, we've really done a good job building a toolkit for computing entropy changes, and we've seen it work across several settings. Let's take some time now to put everything together so we understand the definition of entropy, and we also have an intuition for what our entropy value should be for different scenarios. Again, entropy measures how widely energy is spread among the available molecular energy levels. Microscopically, each complete specification of all particle positions and energies, that is a microstate. Many different microstates can look the same macroscopically, and that collection is a macrostate. At thermal equilibrium, the system is overwhelmingly found in the most probable macrostate, which has the largest number of microstates and the most probable distribution of energy. This molecular interpretation enables us to understand the nature of entropy and its changes. So with this in mind, let's turn back to our examples and start thinking about what entropy value looks like for each of the scenarios. We're going to start with an isothermal gas expansion. At constant temperature, increasing the volume gives each molecule more positions it can occupy. In a larger container, the spacing between translational energy levels decreases, so more of them are thermally accessible at the same temperature. That means the number of microstates increases, and that's why the system's entropy also increases. Because entropy is a state function, that conclusion is independent of whether the expansion is carried out reversibly or irreversibly or as a sudden free expansion. The surroundings, however, they do remember the path. A perfectly balanced reversible expansion leaves the entropy of the universe unchanged overall, whereas an irreversible one produces a positive change in the entropy of the universe. Second, let's think about isothermal mixing of two different ideal gases. When two different gases mingle, each species suddenly has access to the whole combined space, and you're going to have some intermixed configurations with the other species. So the number of distinguishable placements multiplies. So the number of microstates accessible increases, and so does the entropy. We did mention, though, if the two samples are identical, removing that partition creates no new distinguishable arrangements. So the macrostate before and after is the same, and the entropy of mixing is 0 for that specific case. Third, we can talk about chemical reactions. Here, the sign of the system's entropy change really depends on how the reaction redistributes matter across phases and particle counts. Reactions that reduce the number of gas molecules generally reduce the available freedom, and they tend to lower the system's entropy, while reactions that generate additional gas molecules tend to raise it. Shifting material from condensed phases into the gas phase, that will typically increase entropy. Assembling highly ordered condensed products, that tends to decrease it. Now, for the surroundings, the rule is simple. The sign follows the heat flow. So exothermic reactions, they release heat to the reservoir, and therefore they increase delta S surroundings. Endothermic reactions, they draw heat from the reservoir, and therefore they decrease delta S surroundings. Finally, we of course have phase changes. Here I want you to think in terms of freedom of motion. So if you move from solid to liquid to gas, that opens up more accessible configurations, so the system's entropy increases at each step. Moving in the reverse direction from gas to liquid to solid, that's going to remove configurational freedom. So the entropy change at that temperature is going to have a similar magnitude, but negative sign. So in other words, decrease in entropy. In short, entropy tracks how energy and matter are distributed over the available levels and locations. And the second law really helps us decide direction by adding systems and surroundings. And the third law we just described anchors the zero so that absolute entropies and reaction tables all speak the same language. With that, we can now move into our last and final objective. Here we're going to discuss the Carnot engine in great detail. In 1824, Carnot asked a question. What is the greatest efficiency any heat engine can achieve when it operates between a hot temperature and a cold temperature? His insight was that the limit should depend only on those two reservoir temperatures and not on the details of the machine. Now, a heat engine, this is a device that runs in a cycle. Each cycle, it absorbs heat from a hot source, converts part of that energy into mechanical work, rejects the remainder to a cold sink, and then returns to its initial state so that it can repeat. A thermal reservoir, this is simply a very large body whose temperature does not change as it supplies or absorbs heat. We label their fixed temperatures T hot for the source and T cold for the sink. Now, the second law of thermodynamics, it provides us an interesting perspective on all of this. The second law of thermodynamics tells us that a perfect engine is impossible. No cyclic device can take heat from a single reservoir and convert all of it to work. Some heat is always going to be rejected to the colder sink. Carnot's strategy was then to analyze the best case that still obeys the second law. So he thought about an engine that runs through a completely reversible cycle. We model the working substance in this Carnot cycle as an ideal gas that's in a frictionless piston so that every step can be carried out reversibly without friction or other losses. And one Carnot cycle, it's going to have 4 reversible steps. The first is an isothermal expansion at T hot while the gas absorbs heat and does work. The second step is an adiabatic expansion that cools the gas from T hot down to T cold with no heat exchange. The third step is an isothermal compression at T cold while the surroundings do work on the gas and the gas rejects heat to the sink. And then that last step, that fourth step, is an adiabatic compression that raises the gas from T cold back to T hot with no heat exchange, and that closes the cycle. By walking through these 4 segments, we're going to see a really important conclusion. I do want to first state quickly the sign convention here so I don't lose you in all of the math we do to reach that conclusion. So heat into the gas, that's going to be positive. Work done by the gas on the surroundings, that's negative. And for an ideal gas, the change in internal energy depends only on temperature. So any isothermal segment is going to have 0 change in internal energy. With that, let's begin with that first segment from A to B. Here we have an isothermal expansion at the hot temperature T hot. The gas is going to be held at T hot by the hot reservoir while it expands from an initial volume VA to a final volume VB. Because the temperature of an ideal gas is constant, the change in internal energy for this segment is going to be 0. The gas, it must absorb heat to supply the work it does on the piston. The reversible isothermal work for an ideal gas, that's equal to negative nRT times the natural log of final volume over the initial volume. So we can write WAB equals negative nRT hot times the natural log of VB over VA. Now, by the first law, we know that delta U for this segment is equal to 0 because isothermal. So that means the heat equals the negative of the work. So now we can write QAB equals positive nRT hot times the natural log of VB over VA. This is going to be a positive. So in our first segment, you will see that work is negative, heat is positive. Therefore, heat flows in from the hot source and an equal amount of energy leaves as work done on the surroundings. On to the next segment. From B to C, we have adiabatic expansion down to the cold temperature, T cold. So here we thermally isolate the gas so that no heat flows. So QBC is equal to 0. The gas continues to expand and cools from T hot to T cold while doing work. Now, because heat is 0, the work is going to equal the change in internal energy. So for an ideal gas, we can write delta U is equal to work, BC, and that is equal to N times molar CV times delta T, where delta T is T cold minus T hot. This is going to be a negative value. Then we go to the third segment from C to D, and here we have isothermal compression at T cold. We now put the gas in contact with the cold reservoir, and we compress it from VC to VD at a constant temperature T cold. The reversible isothermal work equals negative nRT cold times the natural log of VD divided by VC. Now, VD is going to be smaller than VC. We're going through a compression. So the log is going to be a negative term. And if you multiply the negative log term with the negative sign out front, you're going to get a positive work, meaning work is put into the gas. The rejected heat is going to equal the opposite sign, positive nRT cold times the natural log of VD over VC. Again, that log term is negative. A positive sign multiplied by this negative sign means that the overall quantity for the heat is negative. So the work we put into the gas leaves as heat to the cold sink. Now we make it to our final segment. D to A, we have adiabatic compression back to T hot. We again isolate the gas so no heat flows. That means we write QDA is equal to 0. We compress the gas until its temperature rises from T cold back to T hot. The work here equals the internal energy change, so we can write delta U equals work dA, and that is equal to N times molar CV times T hot minus T cold, which is going to be positive. Because we return to the starting state, the change in internal energy over the whole cycle equals 0. Therefore, the total heat absorbed by the gas over the cycle equals the negative of the total work it does. So we can write work cycle equals negative QAB plus QCD. Now let's connect the pieces to efficiency. Thermal efficiency means useful output divided by required input. The useful output per cycle is the work out. With our sign convention, that's going to be negative work cycle. The required input is the heat that's actually taken from the hot reservoir. And in a Carnot cycle, that happens only on the hot isotherm A to B. So the efficiency is negative work cycle divided by QAB. Because the cycle returns to its starting state, the change in internal energy over the full loop is going to be equal to 0. So that lets us replace negative work cycle with the net heat absorbed over the two isotherms, which is going to be the magnitude of QAB minus the magnitude of QCD. Therefore, the efficiency becomes the magnitude of QAB minus the magnitude of QCD, all divided by the magnitude of QAB, which is the same as 1 minus the magnitude of QCD divided by the magnitude of QAB. To evaluate that heat ratio, we can use the fact that the two adiabatic segments, they tie the volumes together. So both isotherms share the same expansion and compression factor. In fact, it gives us the relationship that magnitude of QCD divided by the magnitude of QAB is just equal to T cold divided by T hot. Plugging that back into our efficiency expression gives the result that efficiency equals 1 minus the cold reservoir temperature divided by the hot reservoir temperature. And this result depends only on the two reservoir temperatures and on nothing else. So from all of this, I want to make some important remarks. First, the reversible Carnot engine. It sets the maximum possible efficiency for any engine that works between a hot reservoir at a temperature T hot and a cold reservoir at T cold. So the best you can ever do in terms of efficiency is going to be 1 minus T cold over T hot, where the temperature is in Kelvin, and you can only reach that limit if every step is perfectly reversible, meaning no entropy is generated anywhere. That leads me to my second point. Real engines never meet that ideal. Finite temperature differences during heat transfer, friction, turbulence, electrical resistance, and mixing all generate entropy. So actual efficiency is always lower than the Carnot value. A 100% engine would require either a cold reservoir at absolute 0 or 0 entropy generation, and both of those are forbidden by the second law. So, no engine can convert all absorbed heat into work. Practically, the only way to really push efficiency up are to raise the hot side temperature, to lower the cold side temperature, and to reduce irreversibilities that are always within material, safety, and environmental limits, of course. With that, we have completed chapter 4. I hope you found it helpful. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day.